Forces on a current-carrying rectangular coil in a magnetic field. Look at the figure. A stiff wire loop, ABCD, is placed in between the poles of a strong magnet. When a current passes through the loop, we will find that there is a turning force on the wire loop. When there is current flowing through the loop, ABCD, the loop will turn about the axis PQ. So we can say that a current-carrying rectangular coil in a magnetic field will experience a turning force. Look at the combined magnetic fields due to the loop and the magnets. The wire AB will have a force acting on one side, while the force on wire CD is acting on the other side. If seen from the viewing end, these two forces produce a turning effect, which turns the loop clockwise. If the magnet or the battery is reversed, the directions of the forces are also reversed. Click on the magnet to reverse its direction and observe. We observe that when the magnet is reversed, the turning force on the loop will be reversed too. Click on any of the wires to reverse the direction of current and observe. We observe that when both the magnet and the direction of current are reversed, the turning force on the loop remains unchanged. Click on the magnet once again to return to its original direction and observe. We observe that when the direction of the current is reversed while the direction of the magnet is kept unchanged, the turning force on the loop will be reversed. This turning effect on a loop of current-carrying wire has a very important application: the motors. The DC motor. The figure illustrates the structure of a simple DC motor. The rectangular loop ABCD of wire is mounted on an axle that will allow it to rotate about the axis PQ. The ends of the wire are connected to split rings X and Y, the commutator. The commutator rotates with the loop. Two carbon brushes are made to press lightly against the commutator. Look at the figure again. Click on the switch to make the current flow through the loop. When the current flows through the loop ABCD, a downward force would act on the left-hand side AB and an upward force on the right-hand side CD. The loop would then rotate about axis PQ until it reaches the vertical position. The current is now cut off, but the momentum of the loop carries it past the vertical position. This reverses the current in the wire arm CD, and now a downward force acts on it. An upward force now acts on the other wire arm AB. Hence, the loop continues to rotate in the same direction. The commutator is there to reverse the direction of the current in the loop whenever the commutator changes contact from one carbon brush to the other. This ensures that the loop will always be turning in one direction. When the terminal of the battery is reversed, the direction of rotation of the loop will be reversed. Click the battery to reverse its direction and observe. The figures show the structure of a simple DC motor and a picture of a motor kit. Click the switch to make the current flow and observe what happens. When current flows through the loop, it rotates. What will be the change in the rotation speed if the loop is replaced by a coil with a greater number of turns? And what will be the change when a stronger magnet is used? If a soft iron core is added, what do you notice? Moreover, if the current is increased by using a battery of higher voltage, do you notice that the rotation speed is further increased? To increase the turning effect or rotation speed of the wire loop, we can 1. Increase the number of turns of the wire in the rotating coil. 2. Increase the current. And 3. Place a soft iron core within the magnetic field lines to strengthen the magnetic field. There are several types of electric motors. These are its important parts. 2 permanent magnets to produce magnetic field. A coil of wire which becomes an electromagnet when current flows through it. 2 brushes which touch onto the coil to let the current flow into and out of the coil.